The objective of this lecture is to determine the properties of the Pn junction, including the high-V characteristics of the Pn junction diode. So the topic is the Pn junction. So in the last class, we looked at the properties of semiconductor materials. We talked about intrinsic, extrinsic, then the mechanisms to create current in a semiconductor. But the real power of semiconductor electronics, it doesn't lie in just when you have the electrons and holes that move, when you have the n-type or the pn semiconductors individually. It lies when the p and the n regions are directly adjacent to one another, forming Pn junction. So in most IC application, you have a single crystal of the semiconductor and one region is doped to be p-type. So the p-type is doped with acceptor impurities and the other region is doped to be n-type. So the n-type is doped with donor impurities. We'll look at the equilibrium Pn junction. So the diagram shows the Pn junction and this diagram shows the doping concentration. So this is the P junction and this is the N junction. The P junction is doped with acceptor impurities. The N junction is doped with donor impurities. For the p-type, the majority carriers are the O's. So and the minority carriers are the electrons. So you can see the concentration of O's is much higher than the concentration of electrons. And for the n-type, the majority carriers are the electrons and the minority carriers are the O's. So you can see the relative gradient of the majority and minority carriers. So this section shows the cross-sectional area of the Pn junction. The interface at x is equal to 0 is the metallurgical junction. So a large density gradient of hole and electrons, it occurs across this junction. So initially, remember we are considering the equilibrium Pn junction. Initially, there's a diffusion of holes from the P to the N region and a diffusion of electrons from the N to the P region. So the flow of holes from the P to the N region, it uncovers negatively charged acceptor ions. So remember that the semiconductor material, it has a net charge of 0. So when the holes they flow to the N region, it uncovers negative charged ions. Conversely, where the electrons they flow from the N to the P region, it uncovers positive charged ions, positively charged donor ions. So this action will create a charge separation, and this charge separation sets up an electric field, and the direction of the electric field is from the positive charged ion to the negative charged ion. So it's from the n-type to the p section. So when no voltage is applied to the Pn junction, remember we are at equilibrium, so that's when no voltage is applied. So the diffusion of holes and electrons will eventually cease, because initially there will be a diffusion which will create the charge separation, but if there is no voltage, that diffusion will cease and the direction of the electric field is going to be reduced as a result, and the direction of the electric field will cause the resulting force to repel the diffusion of holes from the P region and the diffusion of electrons from the N region. So as a result of no voltage being applied, and as a result of the direction of the electric field, the electric field will repel the diffusion of holes from the N region, and will also repel the diffusion of electrons from the P region. So thermal equilibrium will be obtained when the force produced by the electric field and the force produced by the density gradients balance each other. The positively charged region and the negative charged region comprise of the space charge region. So this region here is called the space charge region or the depletion region of the Pn junction. So in this region, there are essentially no mobile electrons or holes. And because of this electric field in the space charge region, a potential difference is present in this region, and this potential difference is called the built-in potential barrier or the built-in voltage. And the built-in potential barrier is calculated by this equation, where kT over E is the thermal voltage and K is the Boltzmann's constant, T is the temperature, and E is the magnitude of the electronic charge. So Na is the acceptor concentration, acceptor atom concentration, Nd is the donor atom concentration, Ni is the intrinsic carrier concentration. So the built-in potential barrier is given by this formula, and is a result, the built-in potential barrier is as a result of the positive charge and the negative charge in the space charge region. And this charge, as we said, it's stationary, it's not moving. So we want to calculate the built-in potential barrier of the Pn junction. We are simply going to use the equation at this temperature with this acceptor atoms concentration and donor atom concentration, and the intrinsic carrier concentration we've gotten previously, and we have arrived at 0.757 volts. So this is the built-in potential barrier across the space charge region. But in practice, this because of this log function, so the built-in potential barrier is not really a strong function of the acceptor or donor atom concentration. So it's like 0.1 or 0.2 volts less than this. So this built-in potential barrier cannot be measured with a voltmeter, because when you put a voltmeter across that space charge region, new potential barriers will be developed across the voltmeter, so cancelling the effect of the built-in potential barrier across the Pn junction. So we'll talk about the reverse bias Pn junction. So we've talked about the first case, which is the equilibrium Pn junction when no voltage is applied. So now, when a reverse bias voltage is applied across the Pn junction, so what does this mean? Reverse bias voltage simply means that a positive voltage is applied to the N region of the Pn junction, while a negative voltage is applied to the P region of the Pn junction. So this applied voltage is going to induce an applied electric field. Note that this applied electric field is different from the one that has already been induced as a result of the space charge region. So it's another one entirely, and the direction of this applied electric field is in the same direction as the one the same as that induced as a result of the space charge region, and the magnitude of this electric field in the space charge region as a result is going to increase above the thermal equilibrium value, because initially you have the electric field as a result of thermal equilibrium, and as a result of applying a reverse bias voltage, another electric field has been induced. So definitely the electric field in the space charge region is going to definitely increase. So this increase in the electric field would hold back the electrons, the holes in the p region and the electrons in the n region, so that there's essentially no current. So no current can actually flow across the Pn junction. So this voltage is called the reverse bias voltage. So when this electric field is increased, as we've said, the number of positive and negative charges in the space charge region will definitely increase, because the doping concentration remains the same. So as a result of the increase in the charge, the width of the space charge region would also increase. So with an increase in the reverse bias voltage, the width of the space charge region increases. So we can see the effects here. So because of the additional positive and negative charge in the space charge region, with an increase in the reverse bias voltage, a capacitance is associated with the Pn junction, and this capacitance is called the junction capacitance or the depletion layer capacitance, because this region is also called the depletion region, and the junction capacitance is given by this equation, where CJO is the junction capacitance at zero applied voltage, VR is a reverse bias voltage, VBI is a built-in potential barrier across the Pn junction. So as a result of this junction capacitance, the voltage across the capacitance cannot change instantaneously. So this would have a significant effect when we are looking at the Pn junction as a switch, because it's not going to switch immediately. So this capacitance voltage characteristics is useful in electrically tunable circuits. So they are junctions specially fabricated for this purpose, and they are called varactor diodes. So we are going to calculate the junction capacitance of a Pn junction at this temperature, with this doping concentration, intrinsic carrier concentration, and this CJO. So we are going to use the same formula we presented, and we got 0.63 volts. Remember, here we're calculating the junction capacitance at this reverse bias voltage and at this reverse bias voltage. So when we apply a reverse bias voltage of 1 volt, we arrive at 0.3 picofarad, and when we apply a reverse bias voltage of 5 volts, we arrive at 0.168 picofarad. So from this, we can say that the magnitude of the junction capacitance is usually within the picofarad range, and it decreases as the reverse bias voltage increase. So the magnitude of the electric field in the space charge region, it increases as the reverse bias voltage increases. So we've already seen this, but the maximum electric field occurs at the metallurgical junction. However, either the electric field nor the applied reverse voltage can increase indefinitely. So at some point, so this electric field that is being increased as a result of the applied voltage and also the reverse bias voltage, this electric field cannot increase indefinitely. At some point, breakdown will occur. So, and a large reverse bias current is going to be generated, which we are going to be seeing later. We talk about the forward bias Pn junction. So there's the third scenario. So in this junction, a forward bias voltage is applied across the Pn junction. So meaning that the negative part of the voltage is applied to the N junction, and the positive voltage is applied to the P junction. So in this case. Now, in this case, remember that there's already an electric field before in thermal equilibrium. So as a result of this forward bias voltage, an electric field is generated, but the applied electric field is in the opposite direction to that in the space charge region, and the net electric field as a result is reduced, but it's always from the N junction to the P junction, though this applied electric field is going to reduce some of it, but the net electric field is going to be in this direction. And as a result of the reduction in the electric field in the space charge region below the equilibrium value, so this is going to upset the delicate balance between the diffusion of the electric field. So as a result of the lowering of the electric field, so the majority carrier electrons from the N region, they diffuse to the P region, and majority carrier holes from the P region, they diffuse into the N region. So this process will continue as long as the forward bias voltage is applied, so creating a current in the Pn junction. So remember, in the reverse bias case, there's not going to be current, no diffusion current is going to be produced, because the increased electric field would repel or will hold back the holes in the P region. It will repel the diffusion of holes, so it will hold back the holes in the P region and to hold back the electrons in the N region. But in the case of the forward bias Pn junction, there's going to be a flow of majority carriers from either region, and a diffusion current is going to be produced. So when a forward bias voltage is applied, so the majority carriers, so as the majority carriers cross into the opposite region, so like the hole here in the P region is the majority carrier, is going to cross into the N region, so thereby increasing the minority carrier in this region. Similarly, the electrons, which are the majority carriers in the N region, is going to diffuse to the P region, so increasing the excess minority carriers, which is the electron in the P region. And as a result of that, there's going to be excess minority carrier concentration in each region, and the excess minority carriers will diffuse into the neutral N and P region when they recombine with majority carrier, thus establishing a steady state condition. So as a result of the forward bias voltage, there will be excess minority carrier in each region, as shown in this figure. So we'll now talk about the ideal current voltage relationship across a Pn junction. So when an applied voltage, so as a result of an applied voltage, it results in a gradient in the minority carrier concentration, and which is going to cause diffusion current. And the relationship between the voltage and the current is given by this equation here. So the current being produced is as a result of the excess minority carrier concentration being because of the gradient in the excess minority carrier concentration. So it is this relationship that describes the relationship between the voltage and the current. So where IS is the reverse bias saturation current, and it's typically within this range. So VD is we can call VD, we can say VD is the built-in uh, potential barrier across the Pn junction. Then VT is the thermal voltage, then the diffusion current being produced as a result. Then VT is the thermal voltage and is specified at 0.026 volts at room temperature. Then this N is quite new. The N is called the emission coefficient or the additive factor, and is usually between the range of 1 and 2, and it depends on the current level. So at low levels it's usually like 1, but when the current is very high, N can be close to 2. And this identity factor emission coefficient, it takes into account any recombination of holes and electrons in the space charge region. So the Pn junction is called a diode. So the Pn junction with nonlinear rectifying current characteristics is called a diode. So when you have the P and the N junction, we say that it's a diode. So we want to calculate the current in a Pn junction diode. So when a forward bias voltage is applied across the junction and a reverse bias voltage is applied across the junction. So with a forward bias voltage VD, we get a current of 4.9 milliamp, but with a reverse bias voltage, we get a current that is essentially close to 0. So this shows we are using the ideal current voltage equation. We're using it to get the current that will flow based on either a forward or a negative or reverse bias voltage is applied. So this is the ideal IV characteristic curve of a diode, of a Pn junction diode. So for a forward bias voltage of approximately 0.7, we can see that the current is an exponential function of the voltage. But when a reverse bias voltage is applied, essentially there is no current that is being produced. And it's important to note that we have this equation for the IV equation of a diode. It's important to note that when VD is greater than 0.1 volts, you can ignore this -1 coefficient. So essentially, we can plot it on a log scale as seen in this equation. So from this figure, as seen in this figure, from this figure with only a small change in the forward bias voltage, the forward bias current increases by order of magnitude, then is essentially a 0 in the reverse bias condition. We can see the diode circuit symbol representation. So it's essentially like an arrow with a diode current flowing in the direction of the arrow. You have the positive side and the negative side at this particular position. So we can use the diode as a voltage control switch that is off when a reverse bias voltage is applied and is on when a forward bias voltage is applied. So because when it is on, a large current is produced, but when it is off, little or no current is produced. So we termed IS as a reverse bias saturation current, and it is gotten as a result of when the diode is reverse biased by at least 0.1 volts. The diode current is equal to minus Is. So when you just plug in this equation, when you have 0.1 here in reverse bias condition minus 0.1 volts, you can see that Is will be approximately equal to minus Is. So that's why we termed it reverse bias saturation current. So the reverse bias saturation current is usually within this range, but it's in practice it may increase to this particular value, but it's still small and it's negligible in most cases. We'll talk about the temperature effect. The saturation, reverse bias saturation current, and thermal voltage, they are functions of temperature, as we can see from the equations that describe them. And since these are functions of temperature, it simply means that the IV characteristic is also a function of temperature in the forward bias condition. So generally, the forward bias voltage decreases as the temperature increases. So this simply means that the voltage that will be required to forward bias the Pn junction is much lower when the temperature is high. So for silicon diodes, it's usually 2 millivolts per degree rise in temperature. We'll talk about the reverse bias saturation current as a function of temperature. So it's also a function of temperature and is a function of the intrinsic carrier concentration. So as we have seen, the intrinsic carrier concentration is dependent on temperature, is strongly dependent on temperature. So the value of Is will double for every 5-degree increase in temperature. So the actual diode current is even much worse. It's going to double for every 10-degree rise in temperature. Because of this effect, you will not really see germanium based diode, because germanium is really sensitive to temperature. So it's really sensitive to temperature. So increase in the reverse current will result in increase in temperature, and it is really very severe in the case of germanium. So germanium is not is impractical. It's not really used for most circuits application because of its sensitivity to temperature. We talk about the breakdown voltage. We've actually mentioned it previously. So we mentioned it when we talked about applying a reverse bias voltage to the Pn junction. So the electric field in its base charge region is going to increase, and the increase in the electric field may become large to a sense that covalent bonds are broken and O pairs are created. So as a result, the electrons are swept in the N region and the O's are swept into the P region as a result of the increase in electric field, and this will generate a reverse bias. This will generate a very large reverse bias current. So this phenomenon is called breakdown. So the reverse bias current generated is limited by the external circuit. So it depends on the external circuitry involved. So if the current is not limited, a large power will be dissipated as a result of the breakdown in the Pn junction, and it may damage the device and cause burnout. But if the circuitry is limited in terms of the currents being supplied, then it may not cause much havoc. So we can see the IV characteristics of a diode in breakdown. So at this point, at this voltage, there is a breakdown. So if the atom is highly doped, the breakdown voltage is going to be, it has a small breakdown voltage. But if it's low doped, the voltage at which the breakdown occurs is much higher. Then we have a phenomenon called the avalanche breakdown. We have several types of breakdown. One is the avalanche breakdown. So the avalanche breakdown occurs uh, as a result of the increase in the carriers in the space charge region. So as a result of the increase in carriers, electric field are generated, and the electric field causes covalent bonds to be broken, and electron hole pairs are generated. So these electron hole pairs, they may gain sufficient amount of kinetic energy as a result of the electric field, and they begin to collide with one another, and this collision results in additional hole pairs being created. So, and it results in avalanche breakdown. So, and this breakdown, like we said, is a function of the doping concentration. So larger doping would result in smaller breakdown voltage. So if the doping concentration is really high, the breakdown voltage is like, it's going to be little, so you would easily reach the breakdown voltage. And the second type of breakdown mechanism is called the Zener breakdown, and is a result of tunneling of carriers across the Pn junction. So, and so that is the kind of breakdown. Then we have a phenomenon called the peak inverse voltage, because different diodes, as we've seen, they have the voltage at which breakdown occurs. So the peak inverse voltage, or the PIV of a diode, must not be exceeded in circuit operation if you want to avoid reverse bias breakdown. So there are certain diodes that are specially fabricated, and they are specially fabricated with a breakdown voltage in mind, and they are designed to operate in the breakdown region. So these diodes are called the Zener diodes. We are going to be discussing it later in this class. We'll now talk about the switching the diode as a switch. So this is the circuit. This is the circuit for the diode being used as a switch. So essentially, this is the switch, and you are switching from the forward bias to the reverse bias case. So we've said that previously. So in reverse bias, it's off, but in forward bias, when a forward bias voltage is applied, it's on. But it doesn't stop there. An important parameter is the transient response, which is the speed and characteristics of the switch, because we've hinted at the junction capacitance, because as a result of junction capacitance, it's not really going to switch instantaneously from either the on to the off or the off to the on state. So we are going to be considering this. So in the first case, when the diode is switched from the on state to the off state, you can see the operation of the circuit here, and the circuit will switch the applied voltage at time t equals to 0 to the forward bias current as a result of switching the forward bias current as a result of switching the transistor on is given by, so the diode current is a forward bias current. So it's given by the applied voltage, the applied forward bias voltage, then VD we can say is the built-in potential barrier across the Pn junction. So that's the potential difference across the Pn junction, and the RF is this RF here. So this is the forward bias current that is produced when the diode is switched on. Then internally, what happens when you switch what happens when you switch the diode on? Well, internally in the P-N junction, you have the P junction and the N junction here. So when the diode is switched on, like we said previously, the O's, they will diffuse from the P region into the N region, increasing the minority carrier concentration of O's in the N region. Similarly, the electrons in the N region, they will diffuse to the P region, so increasing the excess minority carriers of electrons in the P region. So the minority carrier concentration when the diode is switched on, so when a forward bias voltage is applied, is shown in this figure. So the minority carrier concentration is going to increase, and this shaded region shows the excess minority carrier concentration. That's when the diode is switched on. So this excess charge is the difference between the minor carrier concentration for a forward applied voltage and the difference from the reverse bias minority carrier concentration. So essentially, this direction is the minority carrier in reverse bias, when a reverse bias voltage is applied. But this region here is now shows the gradient when the forward bias voltage is applied. So it shows the gradient in the minority carrier concentration when a forward bias voltage is applied. So essentially, when you want to turn off the diode, you need to remove the minority carrier concentration. So when the forward bias voltage is removed, these excess minority carriers, they need to be also be removed, and as a result of them being removed, large diffusion current is created in the reverse bias condition. So when you are switching from reverse bias, when you are switching from forward bias to reverse bias, you need to remove these excess carriers, and as a result, large diffusion current will be produced. And this happens because the excess minority carriers they need to flow back to where they were previously. So this excess minority carriers needs to flow back to the P region, and this excess electrons, they need to flow back into the N region. So when you apply, and that is when you apply a reverse bias voltage. So as a result of that, large diffusion current is produced, and that current, large reverse bias current, is the current is reverse bias because we are switching from on to on. So it's given by the reverse bias current, is given by VR divided by IR. So we've made mention of the junction capacitance. So it doesn't allow the voltage to increase instantaneously. So this reverse current, it's so when you are switching the diode from on to off, we've already seen that a reverse current is going to be is going to be created, and it is associated with a certain amount of time because of one, the excess minority carriers, and two, and the junction capacitance. So the turn off time, the time at which you actually press the switch to turn it from on to off, it's not instantaneous. So the turn off time is equal to the storage time plus the fall time. So what is the storage time? The storage time is the time required for the minority carriers in the space charge region to reach thermal equilibrium. Remember, we are turning the diode off, so their minority carriers, they have to go back to their original position. So you have to take into account the time before they reach equilibrium. Then you have to take into account the fall time. So it's the time required for the current to fall to 10% of its initial value. So it is after that time that the diode will turn off. So similarly, so what it means is that in order for the diode to switch quickly, to switch off quickly, the diode must have small excess minority carriers lifetime. So if the diode is to switch quickly, this excess minority carriers lifetime have to be very short, and you must be able to produce large reverse current poles, because the large current poles will enable it to switch off quickly. So in the design of diode, you must produce a path for transient reverse bias current poles so that it switches off faster. And this is important in computer application, because computers are made up of transistors. Transistors are made up of diodes, and it is diodes that are switching. So as we have the turn off time, so the time to switch from on to off, we also have the turn on time, so the time to switch from off to on. And this is associated with a forward bias current pulse. It turns out that the turn on time, why it's not negligible, it's actually much less than the turn off time. And because in the turn on time, the voltage across the junction, the Pn junction, is gradually increases towards a steady state value. So it's a gradual increase, it's not instantaneous, but it is not exactly zero. It's not like instantaneous, and but it is less than the turn off time. And the reason why it is less than the turn off time, because the turn off time is larger, and it's larger because of the minority, the excess minority carriers, and it's also larger as a result of the junction capacitance. So there is some time, and also a large reverse bias current pulse has to be applied so that that excess minority higher concentration can quickly vanish to their respective position. And also because of the junction capacitance associated with the increase in the number of charges in the space charge region, so that capacitance will not cause the transistor to turn off immediately.